Okay. Good morning. My name is Antonio Sala, and I'm delivering you this talk about my research activity in the last 3 years that is titled Data and Service Integration, Architectures and Applications to Real Domain, under the supervision of Professor Sonia Bergamaschi and Dr. Howard Ho of the IBM Almaden Research Center of San Jose in California. Here's a brief outline of what I'm going to present you. I will give you first a brief introduction and some the motivations that lays behind my work. And I'll present you the MOMIS data integration system, which most of my work is based on. And I divided my presentation into 3 parts that are the main activities I carried on, which can be divided into application of data integration techniques for biology, extension of that integration technique to include service, so to perform data and service integration. And then in the last part of my PhD, I started studying distributed architecture for data integration. So, first of all, data integration is the problem of combining data residing at different sources and providing a unified view of these data. This problem is becoming even more crucial today with the advent of the web, and especially with the Web 2.0, which allows to produce easily a huge amount of data in a collaborative environment, and it makes really easy to share this data. For example, IBM reports that 15 petabytes of data are produced every day on the web, and this is 8 times more than the information stored in all the libraries of the United States, which can give the idea of how big is the amount of data that are produced. So, especially on a web environment, data come from different sources and need to be integrated to provide a thorough knowledge of the information we have available. So, many domains can take advantage of data integration, especially large enterprises. For example, when companies, in the case of companies, mergers and acquisitions, scientific projects, when the results of research are produced by different research units and need to be combined together. In the government domain, when data are produced by different agencies of the government, need to be integrated to have a complete idea of what is going on in that state. And also in the life sciences, for example, after with the genome project, really took great advantage of data integration techniques. So my research was focused on semantic data integration systems, in particular on a mediator-based approach with the MOMIS data integration system. And I studied and developed extensions and applications of this approach in different domains. And I also took into considerations services, as I said before, because with the advent of service-oriented architecture, nowadays are becoming really widely adopted, and are not limited to implement business logics, but also to provide access through web services to informative services, so to the data, which in the so-called data as a service model. So, as I said, most of my work is based on the MOMIS data integration system, which is a framework to perform information extraction and integration of heterogeneous structured and semi-structured data. This has been developed in this university by the DB group of our university. It provides a framework for semantic integration of information based on a common data model, a common object data model called ODLI3, and provides a set of tools to perform the integration, building a global virtual view, the so-called global schema, that gives a global view of the data that are available in the data sources that are integrated. This is a brief sketch of the MOMIS integration process that starts from wrapping the data sources, which means converting all the schema of the data sources in the common data model that is ODLI3, and the elements of the schema of the data sources are then semi-automatically annotated according to a common lexical database that is WordNet in our case, which means every element that appears in the sources is assigned a meaning according to a common ontology of knowledge. This annotation phase is then exploited to create a common thesaurus which stores a set of relationships that can be extracted from the schema of the data sources that we have, and can be of 4 types. Can be derived from the schema, so also the structure of the knowledge of the schemas of the data sources is exploited to derive knowledge. This relationship can also be derived by the lexicon, so exploiting the WordNet, the annotation with regards to WordNet. Can be supplied by the user, the integration designer, or can be inferred with description logic techniques. This common thesaurus is then used to given as input to a clustering algorithm that groups together semantically related concepts appearing in the different data sources to create a global class for each concept of for the main concepts of that appears in the data sources that are integrated, and it creates a mapping table that provides the information about how the local data sources are mapped to the global classes in our global schema. So this system has been applied in the biological domain to create a global schema of different public data sources. Because the problem in biology is that different public data sources are available mostly on the web. These are web databases that need to be, every database provides different information about the same domain. So researchers have the problem of accessing this great amount of data because the databases are numerous, a lot, and they have different interfaces and structures, and usually researchers in the biological domain have low information technology skills. So this project was conducted in the context of the Serial project conducted by the Agrarian Faculty of our University of Modena and Reggio Emilia, and was funded by the government of Emilia-Romagna. And the aim of this project was to perform intelligent data integration of existing databases, which is to create a global schema for the genotypic selection of cereal cultivars. What is the genotypic selection of cereal cultivars? It means to extract genotypic data correlated from phenotypic traits. That means to select a specific, the kind of cultivar to breed based on their phenotypic traits that are expression of their genotypic of their genotype. So this was performed on 3 species with barley and rice. And we integrated existing molecular data sources and phenotypic data sources that, if considered separately, these data provide incomplete information for the genotypic selection of cultivars, and sometimes are overlapping. So what I did mostly, was to extend the MOMI system to face this new domain, and we obtained a global schema that is the first Italian knowledge base that combines molecular and phenotypic data about cereals. And also, I developed a query interface that allows research biologists and breeders, who have really low information technology skills, to query a knowledge base without the need to know any specific query language like SQL or whatever. So the main achievement is the content of this knowledge base, because as I said, it combines genotypic data, molecular data with phenotypic data, and for each, it's important because for each phenotypic trait of a cultivar, the phenotypic evaluations of that trait and the molecular data that express that phenotypic trait. So this is an example of the, this is a screenshot of the graphical interface I developed for this, for the researchers, because they were completely unaware of any query language. So the other part of my work was conducted in the context of the Network Peer for Business project, where the aim of the project was to develop a technological infrastructure to enable companies of any nature, size, and geographic location to search for partners, exchange data, negotiate, and collaborate without limitations and constraints. So what we did in this project was to study and create a network of semantic peers connected to each other by semantic mappings, where each semantic peer exposes a peer virtual view that is a global representation of all the information available in a peer. And this information can be in the form of data, so structured data, structured or semi-structured data, and also multimedia sources, and the services in form of the web services available in that peer. So a peer virtual view is made up of what we call a semantic peer data ontology, which is a global schema built with MOMIs of the data available in the peer, and a global light service ontology, which is a restricted ontology representing all the that is used to describe all the web services available in the peer. So when we talk about data and services, we talk about two different things. Because data provide information about specific needs, while services execute processes involving data and returning other data, so other information. So, but from the user point of view, it's all information. So it means that they both provide information that can be useful to the user. So there's the need to perform what we call an aggregated search that is able not only to identify the data that are answering to a user query, but also the services that are able to operate on them. So, but this is, has always been performed and studied by two different communities, and there's always been the difference between a data search and a service discovery and invocation. So what is needed are new techniques to manage data and services in a unified way. The first time that data and services were considered in the same approach is in the data as a services approach, where web services are provided to give access to the data. So access to data is guaranteed through the service-oriented architecture. But what we proposed was a services as data approach, which is the other way around, where we consider services as as another kind of data sources that can be integrated to the representation of all the data available in our domain to provide to enhance the domain knowledge provided by our global schema of the information. So as I said, data and services have always been studied by different communities, which led to being represented with different models, retrieved and discovered with different techniques, and so forth and so on. But as I said, they provide a complementary vision about the same thing. So, so in our services data approach, we start from a data query, so expressed, for example, in an SQL-like language, and that query is used to retrieve both the data that answer to that query and the services that are related to the query, which express the needs of the user. How we do this? We first create the representation of the of the information we have in our domain. And then we, at query time, we use some techniques to trigger, to extract the terms that are important in an SQL query, and to trigger a service discovery process based on information retrieval, on an information retrieval approach. So, as I said, the peer virtual view is made up of a global light service ontology, and of an SPDO, which is a global scheme of the data built with MOMIS, and a global light service ontology, which is an ontology representing all the terms involved in the description of semantic web services. And we build mappings between these two schemas, and that will be exploited in the at query time. So to build this global light service ontology, we index the terms that appear in the description of semantic web services, and which are referred to some ontologies to provide the shared meaning of these terms. So we index in a information retrieval with an information retrieval approach both the semantic web service description and the ontologies to create a common ontology of these descriptions, which is then reduced for performance reasons, and is then mapped to the representation of the data available in the peer. So as I said, the global light service ontology is built indexing different parts of a web service description, which is the service name, the service description, input, output, precondition, and postcondition. Then all these index terms and the ontology used to provide a shared meaning of to these terms are fused together, and then this big ontology is pruned to reduce its size, because the global service ontology can be really extremely large in size. So that's why we use a global light service ontology. So then the mappings between the semantic peer data ontology and the global light service ontology are discovered applying a modified MOMIS approach, which has been extended and slightly changed, that takes as input the SPDO and the GLSO and their associated metadata, and creates a set of clusters of classes belonging both to the SPDO and to the GLSO, which are automatically discovered, these clusters, and from these clusters we build the mappings, which are the correspondences between the SPDO elements and the GLSO elements. These mappings can then be used at query time for the aggregated search of data and services, where we start from a SQL-like query, like select from where something, and the answer to this query will be a data set from data sources and a set of services that are related to the terms that appear in that query. So, to give an example, if we consider a select name, city, country from accommodation where the city of the accommodation is Modena, we extract from this SQL-like query all the classes in the from clause, all the attributes and the values in the select and where clauses, and all the ranges defined on this in the ontology for these terms. This vector of terms is then we then consider this vector of terms and translate the terms in the terms of the using the terms of the GLSO. So considering the mapping from the SPDO and the GLSO, these terms are then expanded, considering a semantic similarity matrix built in advance to use also synonyms and to consider the similarity between different terms. And this, the final vector that we obtain of terms is then provided to XIII, which is a extended information retrieval engine that is built with Lucene, and on the basis of information retrieval, with an information retrieval approach, it gives back the services that have those terms in their semantic description. So we completely developed this this approach in our prototype, and we evaluated our approach with the OWL test bench for information for semantic web matchmaking, and we had really good results in terms of recall and relatively low precision due to the fact that the benchmark we used to make these evaluations consider as relevant much less documents that those that are really related to the keyword that we were using to retrieve web services. So the last part of my PhD activity, of my research activity, was conducted at the IBM Almaden Research Center of San Jose in California, where I studied the possibility to exploit distributed architecture for data integration, because, as I said, a lot of data is produced nowadays. So that means that data integration approaches will need to consider distributed architecture to cope with this increasing amount of data. So, and we chose for our test case, as our test case, the government domain, because, as you probably know, the Obama administration is really eager to, is making a great effort to exploit the web technologies to disclose the information about what is done with the tax money of the Americans. So, and this amount of this data is a great, really huge data set that it can be interesting to be exploited to to integrate and to see what happens with the tax money in the US. So this was the data sources that we considered that implies members of the United States Congress, the government spendings, the vendor and the companies that were hired to for federal contracts, and the federal agencies that were contracting these vendors for their work. And this was quite interesting because I found that also in the US there's a form of financing that is called earmark that is decided by a Congress member. So the Congress member decide who is the contractor that will win a federal contract, which is kind of weird. So I designed at the IBM Center an ETL-style integration flow realized exploiting open source tools for distributed architectures and data manipulations. I chose the JavaScript object notation as a data representation model, and everything was built on Hadoop, which is a Java framework for data-intensive distributed applications. Most of the clouds that we hear about lately are built on Hadoop. And Hadoop is based on the MapReduce paradigm and enables to develop MapReduce application to work with thousands of nodes and petabytes of data. And I used as data manipulation language Jackal, which is an open source query language developed at the IBM Almaden Research Center, and it works on Hadoop, and it's really flexible, and because it can be extended. It can be extended with defining user-defined functions in Java. So I designed this an integration flow that starts with the extraction and the crawling of data, and different steps, like in an ETL application, for the cleansing and normalization of data, an entity resolution step to deduplicate and join table from tuples from different data sources, and to identify different records, for example, concerning the same contract in different data sources. And I built a search API and user interface indexing all the resulting JSON dataset, and also they asked me to export back from JSON, so from an object representation, the datasets back to a relational database, DB2 in this case, to build an SQL API for business intelligence applications. So this is the architecture of this integration flow that starts from the different data sources, and through different steps performed mostly in Jackal, I obtained a different set of data sets in JSON that can be indexed and that were indexed with Lucene or exported back to a relational version of this table. And I built also a web user interface to search this data. So, as I said, the integrated dataset were made available through different APIs. One was based on a keyword-based search directly on the JSON data, on the JSON version of the data stored in the Hadoop distributed database, distributed file system, sorry, and an SQL API to the relational version of the data for business intelligence application. And these both these interfaces were available also through our web interface. So concluding, I presented you these three parts of my research activity that were, and the main achievement I obtained was in the application of data integration techniques for biology. The most interesting achievement was the ontology that was obtained, because it's the first ontology for the genotypic selection of cereal cultivars that combines both molecular and phenotypic data. In the data as a service, in the data and service integration part of my work, I proposed the services data approach, where semantic services are considered as a kind of data source to be integrated with other data sources to enhance the information, the domain knowledge we have about the considered domain. And finally, I presented an experience in developing an ETL application in a distributed environment, and building a specific APIs for a data as a service approach. So this is a list of my publications, and that's all, if you have any questions.
A very short question, because Antonio was...
With regard to the services data, I have two connected questions. Is the indexing a dynamic process, or
No.
it is a preliminary work? Okay. The second question is about the description. Which kind of description you rely on?
We consider both the WSML. We consider both WSML and AOLS models, but in the test we made, we used AOLS because the benchmark provided AOLS descriptions of the services. Yeah, because there were no semantic web services available in WSML, so it was quite a